ION. The lesson for today is first order differential equations, applications. Now, compound interest continuously interest compounded continuously. P0 is deposit into a bank. P0, P at time 0 and R annual interest rate. Annual interest rate, nominal and annual. i.e. if S means that for $1 for 1 year, interest I equals R. For example, R 6%, okay, $1, 1 year, we have interest I equals 0.06 US dollar. Interest rate per year, 1 year, 1 US dollar. But interest compounded n times per year, compounded n times per year. Compound interest means after each interest payment period, interest I is added into the principal. P after one period becomes to P plus I, and this is the new principal for the next period, compounded. Okay, interest is added into the principal and becomes to the new principal for the next period, and interest for one period R over N. Okay, or nominal annual interest rate per year, but per year n period. So interest for one period R over N. For example, N1 compounded yearly, N2 number of periods of interest payment semi-annually, 6 months, okay, 1 year, 2 periods. N equals 4 quarterly. Okay, and N equals 12 monthly. Compound it yearly, compound it semi-annually, compound it quarterly, compound it monthly. Interest, nominal interest per year, but per year, in 1 year, we have 10 periods of interest payment. So, interest for 1 period is R over N. Okay, and we put P equals PT, accumulated amount of money at time T. Okay. Now, begin this period. The principal is P at time T, and interest for 1 period. We have P times R N. Okay, time equals P, principal at beginning of this period, times interest for 1 period. So we have delta P equals P R over N equals P R delta T. Delta T is 1 over N. Delta T 1 over N. Okay. Now, when N tends to infinity, number of periods interest payment tends into infinity. We have continuously compounded. Continuously. Okay, and we use the notation D instead of delta. dP equals P R dt, or dP over dt equals Rp. dP over dt equals Rp. Now, separating variables, P in the left hand side and T in the right hand side. We have dP over P equals R dt. And integrating both sides is integrating dP over P R integral dt. Okay, R is a constant, positive constant. Move to outside of integral. And we have natural log of P positive equals R T integral differential inverse. They are inverse each other. So we have T plus C. Now move the function natural log to the right hand side. It become inverse. Log is exponential to the base e r t plus c e. Move the function natural log to the right side, it becomes its inverse function, exponential to the base e, equals e power c times e power rt. Okay. Now at t equals 0, we have p is p0 and e power c e power 0 1. So the right hand side is ac. So we have p here equals ec p0. This is the formula for the case of compounded continuously. P accumulated amount at time t equals P0 origin principle e power rt or annual interest rate. Now consider some example. Now the height of a tree increases continuously at the rate of R 10%. How many years will it take for the height to double, to triple? Okay. We have the formula P equals V0 e power RT. Here are V0 e power 0, 1, 10 T. Now double. V is 2 V0, 2 V0. Double. And 2 equals e power 0, 1, 10 T. This is an equation for unknown T. Move the function exponential to the base e. To the left hand side, we have inverse function, natural log of 2, 0, 1, 10 T. And T equals log 2 over 0, 1, 10. Okay, and use your pocket calculator. We have the result 6.9. Yes. Okay. Now B. Question B. Triple. 3P 0 triple equals P0 P power 0.1 T. 3 equals P power 0.1 T. Move the function exponential to the base e. To the left hand side, we have its inverse function, natural log, and T equals log 3 over 0.1 approximately equals 10.9 years. Okay, very easy. Use this formula. Double 2 V0 triple 3 V0. Exponential growth. Exponential growth. And population. N equals N times T population. We have population growth is continuous and exponential. So we have the same formula. We have P here N equals N0 e power k t, and population. N0 is N at T 0. And K here positive growth constant. Okay, growth constant instead of annual growth rate for continuously compounded. Now consider some example. The population in 1970 was 125,000. In 1990 was 140,000. The question is the population in 2000 and is what? Okay. Solution. Use this formula here. We put T 0 is 1970. Okay, and we have 1990 T equals 20 and 2000 T 30. Okay, we have N0 and at T0 here 125,000. So N equals N0 e power KT equals 125,000 e power KT. Now in 1990, we have at T equals 20 and so 140,000 substitute into this equals rewrite e power k t t here So move to the left hand side. Multiplication becomes to division. E power 20k. And move the function exponential to the base e to the left hand side. It becomes inverse function, natural log. Okay, and move this to the left hand side. We have multiplication becomes to division. Okay. Okay. Move the function e power to the left hand side. We have the function natural log. And move 20 to the left hand side. We have 1 over 20. So k is okay. Is now another example. How many years? How many years will a population double if it triples in 81 years? It tripled in 21 years. How many years will a population to double? Solution. We have the formula capital N equals capital N0 e power k t. Okay. Triple in 81 years. Triple 3 and 0 equals N0 e k times 81 and 3 e delete 3 rewrite and move the function exponential to the base e to the left hand side. We have natural log of 3 and move its factor multiplication to the left hand side. We have division equals k, and we can find k equals k natural log of 3 over 81. Now double to n 0 equals n0 e power k here log 3 over 81 t log 3 over 81. T. Delete. We have 2 e power okay. To find T, we have to move this function to the left hand side. Its inverse function, natural log of this, and move this factor to the left hand side. We have inverse of this 81 over log 3 equals T. Use your pocket calculator. We have T. $51.1 years. Okay. Triple 81 years. Double 51.1 years. Now exponential decay. Exponential decay. Okay. The radioactive decay is continuous and exponential. The radioactive decay is continuous and exponential. N is an at time T amount of radioactive substance, and lambda positive decay constant. Similarly, we have N equals N0, N at time 0 times e power minus because increase, not decrease, decay, minus lambda T. Similarly, because it's continuous. Now, consider some examples. Find the decay constant. And the half-life. If 60% remains after 50 days, 50%, 60% remains after 50 days. Half-life the time for radioactive substance to decay 1/2 half-life. The time for the radioactive substance to decay 1/2 is called half-life. First, we find the formula for half-life. Decay 1/2 N0 over 2 here equals N0 e power minus lambda t. Half-life here t. We have delete 1 over 2 e power. Move to the function exponential to the base e. We have its inverse function, natural log. We write this, and natural log of 1 over 2 is minus log 2. Okay, and t equals log 2 over lambda, half-life. Okay. Time for radioactive substance decay 1/2 is called half-life. Now, 60% remains. 60%, 0.6 and 0. Okay, equals N0 e power minus lambda t. T here 50 days. Remain 60%. Okay, and delete. Natural log move e to the left hand side. We have log here minus 50 lambda, and lambda is log 0.6 over minus 50. You can use pocket calculator. Natural log. Okay. Zero, one, lambda. Decay constant, positive. And the formula for half-life here, T equals log 2 over lambda. You can use your pocket calculator. We have 67.8 days. Means that after 67 18 days. The radioactive substance decay 1/2. Okay, half-life. Now estimating the age of an ancient tree. Ancient tree. For a tree, we have 14 carbon-14 decays when the tree dies, and carbon-12 constant. Carbon-14 decays when the tree dies, and carbon-12 constant. So, by comparing the ratio carbon-14 divided by carbon-12 of the ancient tree, compare with carbon-14 divided by carbon-12 of a similar tree that is alive today, ancient today. We have, because this constant, so we have carbon-14 over ancient over carbon-14 today, because this and this constant. So the ratio divided this, the ratio equals the ratio of this and this ancient tree. And we have half-life of carbon-14 5,730 years. Now consider an example. Even this is 0.6 of this today. Find the age of ancient tree. Solution. we have this equals 0.6 of this, means this equals 0.6 of this. Okay, means that N0 tension equals 0.6 tension equals 0.6 N equals 0.6 of N0. Okay, and this equals 0.6 of today, N0, N0. So we use the formula N equals N0 T power minus lambda T, similar to above formula. N equals N0 times E power minus because decay, increase, not decrease. Now substitute N 0.6 N0 E power minus lambda T, or 0.6 E power minus lambda T is natural log of 0.6, and T equals natural log of 0.6 over lambda. Okay, but we have the half-life. We have the half-life. The half-life. Log 2 over lambda equals years. So lambda equals, lambda move to the right hand side and this move to the left hand side. Log 2 over equals. Okay. Substitute this into this. We have T, the age of ancient 3, T equals log 0.6 over lambda log 2 over, and you can use pocket calculator. We have 4,223 years. Okay. Now we choose in power parity. model, which is in power parity model. V1 domestic price index. V2 foreign price index. Taiwan domestic inflation rate IE. P1 is P1 prime is P1 P1. Inflation means that. Similarly, we have V2 foreign inflation rate, foreign IE P2 prime equals pi 2 P2. Now we put S, capital S, E, exchange rate. Equals P1 over P2. P1 over P2. Now we have S, capital S, E prime equals P1 over P2 prime equals P1 prime P2 minus P1 P2 prime over P2 square equals this here P1 pi 1 P1 P2 and minus P1 here pi 2 P2 over P2 square and delete we have P1 pi 1 P1 pi 1 P1 over P2 and here delete pi 2 P1 over P2. Okay, this is similar to the previous case. Equals pi 1 minus pi 2 capital S E. Capital S E D capital S E over DT equals pi 1 minus pi 2 times capital S E. Similar to the previous cases. So we have capital S E equals E power is pi 1 minus pi 2 T. Okay. That's all for the course. Thank you.